Welcome to a moment in human history where one question, older than civilization itself, is being asked again with sharper eyes and deeper evidence than ever before. How big is the universe, really? Not how far we can see, not how old the light is, but the true scale of everything that exists. And for the first time, data from the James Webb Space Telescope is forcing scientists to reconsider the answer. For thousands of years, humanity has looked upward and tried to measure the immeasurable. Ancient astronomers mapped the stars believing they were fixed lights embedded in a cosmic shell. Later generations discovered planets, then galaxies, then the vast expansion of space itself. Each discovery expanded our sense of scale. Yet each time, we believed we were approaching the limits of what could be known. Again and again, the universe proved larger than expected. Today, we stand at another of those moments. The question of the universe's size is deceptively simple. It sounds like something that should have a number attached to it, a boundary that could be traced, a final distance that could be written down. But the universe does not cooperate with human intuition. It does not present itself as an object sitting in space. Instead, it is space, stretching, expanding, and carrying galaxies along with it. For decades, astronomers relied on the concept of the observable universe. This is not the entire universe, but the portion of it from which light has had time to reach us since the beginning of cosmic expansion. Based on the age of the universe, about 13.8 billion years, and the speed of light, scientists calculated a visible boundary when that boundary was thought to span roughly 93 billion light-years in diameter. That number became familiar. It appeared in textbooks, documentaries, and simulations. It felt enormous, comfortably incomprehensible. And for a while, it seemed stable. Then James Webb began sending back data. What Webb has done is not simply see farther in a trivial sense. It has looked deeper into cosmic time with unprecedented clarity. It has detected galaxies that appear far more massive, far more structured, and far more evolved than existing models predicted for such an early universe. These observations do not merely add details to the picture. We already had details. They challenge the scale of the picture itself. To understand why, we need to return to the basic idea of distance in the universe. In everyday life, distance is straightforward. A kilometer today is the same as a kilometer tomorrow. But in the cosmos, distance is entangled with time and expansion. When we look at a distant galaxy, we are not seeing where it is now. We are seeing where it was when the light left it. And during the billions of years that light traveled, space itself expanded. This means the universe is larger now than the distance the light actually traveled. For years, astronomers accounted for this expansion using well-tested models. They assumed certain rates for how fast space has stretched over time. Those rates fed directly into calculations of size. But James Webb's observations suggest that something about those assumptions may be incomplete. Webb has identified galaxies at extreme distances whose brightness and structure imply rapid formation. According to earlier models, these galaxies should not exist yet. Not in the form Webb sees them. They appear too massive, too organized, too early. This creates a tension. Either galaxies formed much faster than we thought, or the universe expanded differently than we assumed, or both. And if expansion behaved differently, then our estimates of distance, and therefore size, must change. This is where the idea of the actual size of the universe becomes more complex and more interesting. Webb is not drawing a line around the cosmos. It is not showing an edge. Instead, it is refining the ruler we use to measure everything else. When that ruler changes, every distance recalculated with it changes as well. What makes this moment especially significant is that James Webb operates primarily in infrared light, and this allows it to detect ancient light that has been stretched by expansion beyond in the visible spectrum. Galaxies that were once invisible to previous telescopes suddenly become measurable. Their redshifts, how much their light has been stretched, can be analyzed with greater precision. Redshift is not just a technical detail. It is the key to cosmic scale. The more a galaxy's light is stretched, the more space has expanded since that light was emitted. Redshift tells us how far back in time we are looking and, indirectly, how much the universe has grown since then. Webb's measurements suggest that the early universe may have been more efficient at building structure than expected. That efficiency hints at a universe that may be larger, possibly much larger, than earlier conservative estimates implied. But this does not mean previous science was wrong in a simple sense. It means it was incomplete. Every generation of astronomy has worked with the best instruments available at the time. Each generation has revised the universe upward in size. There is no reason to assume this process has ended. In fact, history suggests the opposite. When Galileo first pointed a telescope at the sky, he discovered moons around Jupiter and stars invisible to the naked eye. The universe instantly grew. When Edwin Hubble discovered that galaxies lay beyond the Milky Way, the universe expanded again. When astronomers discovered cosmic expansion itself, the idea of a static universe collapsed entirely. James Webb belongs to this same lineage. It is not just another telescope. It is a scale shifter. The phrase, actual size of the universe, must be handled carefully. Scientists are precise with language for a reason. Webb has not measured the total universe. That may be infinite or finite, but unimaginably vast. What Webb has done is reveal that the observable portion, the part we thought we understood, may be larger and more complex than previously believed. This distinction matters. The observable universe is not a physical boundary. It is a limit imposed by time and light. Beyond it, there may be more galaxies, more structure, perhaps even endless repetition. Webb cannot see beyond that horizon. No instrument ever can. But by refining how we understand expansion, Webb indirectly reshapes what that horizon means. If the universe expanded faster in certain early phases than we thought, then the light we see today has traveled through a greater amount of stretched space. That implies the universe's present-day size could be significantly larger than earlier models suggested, even if its age remains the same. This realization is subtle, but profound. It means the universe may not just be bigger by a small correction. It could be bigger by orders of magnitude beyond the observable limit. The observable universe could be a tiny bubble within a far larger reality, one we can infer mathematically but never observe directly. James Webb did not set out to answer this question explicitly. It was designed to study star formation, galaxy evolution, and exoplanet atmospheres. But science often advances not by direct intention, but by consequence. By seeing the early universe more clearly, our Webb forces us to revisit foundational assumptions. And when foundational assumptions change, everything built on top of them must be re-examined. This is why headlines proclaim that James Webb has revealed the actual size of the universe. Not because it delivered a final number, but because it exposed how incomplete our previous estimates were. It showed that the early universe was not simple or sparse. It was already rich, already structured, already vast. That richness implies scale. What do we mean by the size of the universe? Before any measurement can be trusted, the question itself must be clear. When people ask about the size of the universe, they often imagine a container, something with an edge, a center, and a boundary beyond which nothing exists. This intuition comes from everyday experience, where objects occupy space rather than being space. The universe, however, does not behave like an object inside a larger room. It is the room itself, expanding in all directions at once. This distinction is critical, because the universe does not offer a single, simple definition of size. Instead, there are multiple meanings layered on top of one another, each correct within its own framework. Confusion arises when these meanings are blended together, or when everyday intuition is applied to cosmic scales where it no longer works. The most commonly cited measure is the observable universe. This refers to the region of space from which light has had enough time to reach us since cosmic expansion began. Because the universe is about 13.8 billion years old, it might seem reasonable to assume that we can see out to a radius of 13.8 billion light years. But this assumption is wrong in a subtle and important way. While light travels at a constant speed, space itself expands. When a distant galaxy emitted the light we detect today, it was much closer than it is now. During the billions of years that light was traveling toward us, the space between us and the galaxy stretched. As a result, the galaxy's current distance is far greater than the distance the light actually traveled. When this expansion is accounted for, the radius of the observable universe grows to about 46.5 billion light years, giving a diameter of roughly 93 billion light years. This is not a guess. It is a calculation based on cosmic expansion models that have been refined over decades using multiple lines of evidence. Yet even this number does not represent the full universe. It represents a horizon, an information boundary. Beyond it, there may be galaxies, stars, and structures just as real as those we can see. But their light has not had enough time to reach us. They are not absent. They are simply inaccessible. This is where the idea of the total universe enters. The total universe includes everything that exists, whether observable or not. Its size may be finite or infinite. Current observations strongly suggest that space is geometrically flat on large scales, which implies that the universe may be infinite, or at least vastly larger than the observable portion. If the universe is infinite, then the question of total size has no numerical answer. There is no edge to measure. In that case, the observable universe is just a tiny region within an endless expanse, like a flashlight beam illuminating a small patch of fog in every direction. Even if the universe is finite, its size could still be so large that the observable universe represents an insignificant fraction of it. In both scenarios, what we see is not representative of the whole. It is a local sample constrained by time and light. This leads to a crucial realization. When scientists talk about the size of the universe, they are often talking about the size of the observable universe, not the universe itself. This is not a limitation of technology alone. It is a limitation imposed by the speed of light and the age of the cosmos. James Webb does not remove this limitation. No telescope can. And what Webb does is refine our understanding of how big the observable universe is now and what that implies about the universe beyond it. To appreciate why Webb's data matters so much, we must also understand another key concept. Cosmic expansion is not uniform over time. The universe has not expanded at the same rate throughout its history. In the early universe, expansion was extremely rapid. Later, it slowed. More recently, it began accelerating again due to dark energy. Because of this changing expansion rate, distance calculations depend heavily on assumptions about early cosmic behavior. Small adjustments to those assumptions ripple outward, altering estimates of size by enormous amounts. This is why the discovery of unexpectedly massive early galaxies is so disruptive. If these galaxies formed earlier or faster than predicted, then the timeline of expansion may need adjustment. And if expansion behaved differently, then distances derived from that expansion must be reconsidered. It is also important to distinguish between co-moving distance and proper distance. Co-moving distance measures how far objects are from one another when the expansion of space is factored out, effectively freezing the universe at a specific cosmic time. Proper distance, on the other hand, measures how far apart objects are right now, including the effects of expansion. When scientists say the observable universe is 93 billion light-years across, they are referring to proper distance today. The light itself did not travel that far, but the space it moved through expanded during its journey. James Webb's observations refine how we translate redshift into these distances. A redshift tells us how much the universe expanded while light was in transit. Webb measures redshift with exceptional precision, especially for extremely distant objects whose light has been stretched into the infrared. The clearer these measurements become, the more confident scientists can be in mapping cosmic scale. And as that map sharpens, it increasingly suggests that earlier estimates were conservative. There is another layer to this discussion that often goes unrecognized. The universe has no center. Expansion occurs everywhere at once. From any galaxy's perspective, other galaxies appear to be moving away. This means the observable universe is centered on the observer, not on any absolute location. If intelligent observers existed in a galaxy billions of light-years away, they would measure an observable universe centered on themselves, just as large as ours, yet containing a different set of galaxies. There is no privileged viewpoint. This symmetry implies that what we observe locally may repeat endlessly beyond our horizon. This repetition does not mean exact copies of Earth or humanity necessarily exist, but it does suggest that the large-scale structure of the universe extends far beyond what we can access. Webb's discoveries strengthen this implication by revealing complexity at the very edge of what we can see. Another common misconception is that the observable universe grows because light travels farther with time. In reality, it grows because the universe ages. As time passes, light from more distant regions has time to reach us, expanding the horizon. But this growth is limited by cosmic expansion. Some regions will never become observable because space between us and them expands too quickly. This introduces the idea of a cosmic event horizon, beyond which events will never be observable, no matter how long we wait. James Webb helps refine where this horizon lies by improving our understanding of expansion dynamics. All of this means that the phrase "actual size of the universe" must be interpreted carefully. It does not mean a final measurement. It means a better understanding of scale. How large the universe must be to produce what we observe. James Webb's contribution lies in forcing that scale upward. By seeing large, mature galaxies at times when the universe was supposedly young, Webb implies that the universe either expanded differently, formed structure faster, or both, and each possibility pushes size estimates outward. The universe is not simply bigger because we see farther. It is bigger because the story of its early growth appears richer and more complex than expected. Richness requires room. Complexity requires time and space. Webb is showing us both. Before James Webb, what we thought we knew, long before the James Webb Space Telescope ever unfolded its mirrors in space, astronomers believed they had a reasonably solid understanding of the universe's size. That confidence did not come from a single observation or instrument, but from decades of layered measurements. cross-checked using different methods and technologies. The picture seemed consistent. The numbers aligned. The margins of error appeared manageable. And for a time, the scale of the cosmos felt settled. At the center of this earlier understanding stood the Hubble Space Telescope. Launched in 1990, Hubble transformed astronomy in ways that are difficult to overstate. It did not merely improve resolution. It extended humanity's vision beyond the limits of Earth's atmosphere, allowing astronomers to observe distant galaxies with unprecedented clarity. For more than 3 decades, Hubble shaped our cosmic worldview. Hubble's most famous contribution to cosmic scale was its role in refining the expansion rate of the universe. By observing distant galaxies and measuring how their light shifted toward the red end of the spectrum, astronomers could determine how fast those galaxies were moving away from us. This expansion rate, often called the Hubble constant, became a cornerstone of distance calculations. To understand why this mattered, it helps to think of the universe as a stretching fabric. The faster that fabric stretches, the farther apart galaxies become over time. If you know how fast space is expanding and how long it has been expanding, you can estimate how large the observable universe should be today. Hubble provided data that allowed astronomers to do exactly that. By studying a class of stars known as Cepheid variables, stars whose brightness varies in a predictable way, Hubble helped calibrate cosmic distances. Cepheids act as standard candles, objects whose true brightness is known. By comparing how bright they appear from Earth to how bright they actually are, astronomers can calculate their distance. Once Cepheids were used to measure distances to nearby galaxies, those measurements could be extended outward using brighter objects such as supernovae. When this step-by-step approach became known as the cosmic distance ladder, each rung depended on the accuracy of the one below it. For decades, this ladder seemed sturdy. Using these tools, astronomers converged on a consistent picture. The universe was expanding. It was about 13.8 billion years old. And when expansion was factored in, the observable universe had a diameter of roughly 93 billion light years. This number became widely accepted not because it was simple, but because it was supported by multiple independent methods. Another pillar of this earlier model came from observations of the early universe itself. The cosmic microwave background, the faint afterglow of the hot early universe, provided a snapshot of conditions shortly after cosmic expansion began. Measurements of tiny temperature fluctuations in this background radiation revealed information about the universe's composition, geometry, and expansion history. These observations suggested a universe that was remarkably uniform on large scales. Matter appeared evenly distributed. Space appeared geometrically flat. Expansion appeared well-behaved. When these data were combined with Hubble's distance measurements, the resulting model was elegant and internally consistent. Within this framework, the early universe was thought to be relatively simple. The first stars formed after hundreds of millions of years. The first galaxies emerged gradually, growing through mergers and slow accumulation of matter. Massive, well-structured galaxies were expected to appear much later in cosmic history. This expectation was critical, where it set the timeline against which all distant observations were interpreted. If a galaxy appeared at a certain redshift, astronomers could estimate how old the universe was at that time and what kinds of structures should exist. The farther back one looked, the smaller and less evolved galaxies were expected to be. Hubble largely confirmed this picture within its limits. Its deepest images, such as the Hubble Ultra-Deep Field, revealed thousands of distant galaxies packed into tiny patches of sky. These images pushed observational astronomy close to its limits, showing galaxies as they were billions of years ago. But Hubble had a constraint that could not be overcome. It observed primarily invisible and near-ultraviolet light. As the universe expands, light from distant objects is stretched, shifting it into longer wavelengths. And at extreme distances, this light moves out of the visible range entirely and into the infrared. This meant that the most ancient galaxies, the ones formed closest to the beginning of cosmic time, were effectively invisible to Hubble. Astronomers knew this limitation well. They accounted for it. But they also assumed that the unseen galaxies beyond Hubble's reach would behave in ways consistent with existing models. In other words, there was an assumption of continuity. What lay just beyond the observational limit was expected to resemble what lay just inside it, only slightly earlier and slightly simpler. That assumption turned out to be fragile. Before Webb, size estimates of the universe depended heavily on how quickly structure formed in the early cosmos. If galaxies formed slowly, then early space was relatively empty, and expansion models fit neatly. If galaxies formed rapidly, then early space had to accommodate more matter, more energy, and more complexity sooner than expected. The pre-Webb consensus favored slower formation. This was not arbitrary. It was supported by simulations of cosmic evolution that matched observed large-scale structures. These simulations relied on known physics, gravity, dark matter, radiation, and the expansion of space. They reproduced the universe we saw, up to a point. But simulations are only as good as their assumptions. One of those assumptions involved the behavior of dark matter in the early universe. Dark matter provides the gravitational scaffolding upon which galaxies form. If dark matter clumped more efficiently or earlier than expected, then galaxies could form faster and grow larger earlier in time. Another assumption involved the rate of cosmic expansion during the universe's first few 100 million years. Small differences in early expansion rates have enormous downstream consequences. A slightly faster early expansion means vastly more space today. Before Webb, these early parameters were constrained indirectly. Astronomers inferred them by working backward from later observations. The approach was logical, but it left room for hidden complexity. This is where the earlier picture of the universe's size begins to show its limits. The observable universe's diameter was not a directly measured quantity. It was a derived one. It depended on expansion history, which depended on early conditions that had never been observed directly. Hubble brought astronomers close to the edge of that unknown region, but it could not cross it. As a result, the accepted size of the universe was best understood as a minimum. It represented how large the universe had to be to produce what we observed, not necessarily how large it actually was. This distinction was acknowledged within the scientific community, but it was rarely emphasized in public discussions. Numbers like 93 billion light-years took on a sense of finality they were never meant to have. The arrival of James Webb changed this situation by removing the veil over the earliest observable epochs. For the first time, astronomers could directly observe galaxies forming within the universe's first few 100 million years. And what they saw did not align neatly with expectations. The galaxies Webb detected were not faint, irregular smudges. Many appeared surprisingly bright, massive, and structured. According to earlier timelines, such galaxies should not yet exist. Their presence suggested that something about the early universe had been underestimated. And when the early universe is underestimated, the size of the universe is underestimated with it. Before Webb, astronomers believed they had reached a plateau in understanding cosmic scale. The numbers seemed to converge. The uncertainties seemed manageable. The universe felt mapped. What Webb revealed is that the map was missing entire regions, not because of carelessness. Why James Webb changes everything. The shift in our understanding did not come from a single surprising image or an isolated discovery. It came from the nature of the instrument itself. The James Webb Space Telescope was not designed to simply improve on previous telescopes. It was designed to operate in a fundamentally different way, targeting a region of the universe that had remained largely inaccessible until now. To understand why Webb is so transformative, it is important to understand what limits earlier telescopes faced. The most distant galaxies do not disappear because they are faint alone. They disappear because their light changes. As the universe expands, light traveling through space is stretched to longer wavelengths. This stretching moves ancient light out of the visible spectrum and into the infrared. Earlier space telescopes, including Hubble, were optimized primarily for visible and near-ultraviolet light. They could peer deep into space, but only up to a point. Beyond that point, the universe did not become empty. It became invisible to those instruments. This is the gap Webb was built to cross. The James Webb Space Telescope was engineered from the ground up to observe the universe in infrared wavelengths. This choice alone reshaped what could be seen. Infrared light carries information from the earliest stars and galaxies, whose radiation has been stretched by billions of years of cosmic expansion. Where visible light telescopes see darkness, Webb sees structure. Webb's mirror is another critical factor. At over 6 meters across, it is the largest mirror ever launched into space. This size allows it to collect far more light than any previous space telescope. More light means greater sensitivity. Greater sensitivity means faint. Distant objects become measurable rather than speculative. But size alone is not the full story. Webb's mirror is segmented and precisely aligned. It's allowing it to maintain optical accuracy even as temperatures change. This precision matters because infrared observations are extremely sensitive to heat. Even small thermal fluctuations can overwhelm faint cosmic signals. To address this, Webb was placed far from Earth, at a stable gravitational location where it could remain shielded from heat and light. A massive sun shield protects the telescope, allowing its instruments to cool to temperatures where infrared detection becomes possible. In this cold, dark environment, Webb can detect light that left its source billions of years ago. This design gives Webb a unique advantage when studying the early universe. It does not just detect distant objects. It resolves them. It distinguishes between faint background noise and actual structure. It measures spectra, detailed breakdowns of light that reveal composition, motion, and distance. Spectroscopy is central to Webb's impact on cosmic scale. By analyzing how specific wavelengths are stretched, astronomers can determine redshift with high precision. Redshift is not simply a measure of distance. It encodes the expansion history of the universe between the time the light was emitted and the time it was received. Earlier telescopes often relied on indirect estimates for extreme distances, combining brightness assumptions with models of galaxy formation. Webb reduces reliance on assumptions by providing direct spectral measurements for objects at unprecedented redshifts. This matters because the farther back in time one looks, the more sensitive conclusions become to small errors. At extreme distances, even a tiny miscalculation in redshift can translate into billions of light years of difference in present-day distance. Webb tightens those uncertainties. When astronomers began analyzing Webb's first deep-field images, they immediately noticed something unexpected. Galaxies appeared at redshifts corresponding to times when the universe was thought to be extremely young, only a few 100 million years old. Yet these galaxies were not faint or chaotic. Many showed signs of mass, structure, and chemical maturity. This was not a single anomaly. Multiple observations pointed in the same direction. The early universe appeared more developed than predicted. This created a problem, not just for galaxy formation theories, but for the timeline used to calculate cosmic size. If galaxies formed earlier, then matter clumped earlier. And if matter clumped earlier, then gravitational structures existed sooner. And if structures existed sooner, then the universe had to provide sufficient volume to accommodate them. Volume implies size. Webb does not directly measure the universe's full extent, but by revealing that the early universe was already rich with structure, it forces a re-evaluation of how much space existed at those early times and how much expansion has occurred since. This is where Webb's impact on size estimates becomes unavoidable. Expansion history is the bridge between early observations and present-day scale. Change the history, and the scale changes with it. Another crucial contribution from Webb is its ability to peer through cosmic dust. In the early universe, star formation was intense, producing clouds of dust that absorb visible light. Infrared light passes through this dust, allowing Webb to see regions that were previously hidden. This means earlier telescopes may have underestimated the number and size of early galaxies simply because they were obscured. Webb reveals that the early universe was not just active, it was crowded. Crowding at early times again points to scale. A universe that is too small cannot produce widespread, massive structure so quickly without violating physical constraints. Webb's data suggests that the universe had room to grow, more room than earlier models comfortably allowed. Importantly, these findings do not overthrow established physics. They challenge assumptions within existing frameworks. The laws governing gravity, light, and expansion remain intact. What changes is how those laws played out in the universe's first moments. And Webb's observations suggest that either expansion proceeded differently in the early universe, or that matter behaved in ways that allowed faster structure formation. Both possibilities have implications for size. This is why headlines emphasize actual size. It is not because Webb drew a boundary. It is because Webb removed a blindfold. It allowed astronomers to see parts of the cosmic story that were previously inferred but never observed. With those observations now in hand, the universe appears less empty in its youth, more complex earlier, and therefore larger in its present form than conservative estimates implied. As the data continues to be analyzed, models are being refined rather than discarded. But refinement itself moves the scale outward. Each correction compounds. Each adjustment stretches the cosmic ruler. How James Webb turns light into distance. To understand why James Webb's observations affect the perceived size of the universe, we need to look closely at how distance is actually measured in cosmology. Astronomers do not measure cosmic distances the way distances are measured on Earth. There is no ruler that stretches across space, no direct way to mark endpoints. Instead, distance is inferred from light, how it behaves, how it changes, and how long it has traveled. The most important concept in this process is redshift. When light travels through expanding space, its wavelength stretches along with that space. Shorter wavelengths shift toward longer ones, moving from blue toward red, and eventually into the infrared. The more space expands during the light's journey, the more pronounced this stretching becomes. So redshift is a direct record of how much the universe has expanded since the light was emitted. James Webb excels at measuring redshift because it observes in infrared wavelengths, precisely where the most ancient light now resides. Light that left its source as ultraviolet or visible radiation billions of years ago arrives today stretched into the infrared. Earlier telescopes struggled to detect this light clearly. Webb was built for it. Redshift is often represented by a simple number, but its implications are far-reaching. A higher redshift means we are looking further back in time, closer to the beginning of cosmic expansion. It also means that the object we are observing is now much farther away than it was when it emitted the light we see. This creates a subtle but essential distinction. Though there is a difference between how far the light traveled and how far away the object is now. Webb's measurements help clarify this difference by providing more accurate redshift data for extremely distant objects. However, redshift alone does not give distance directly. It must be interpreted through a model of how the universe has expanded over time. This is where assumptions enter the process. Cosmological models describe how fast the universe expanded at different stages in its history. These models incorporate the effects of matter, radiation, and dark energy. When astronomers observe a galaxy's redshift, they plug that value into a model to determine how much space has expanded since the light was emitted. From this, they calculate distance. And if the expansion rate used in the model is even slightly off, especially in the early universe, the resulting distance can be significantly wrong. At extreme redshifts, small differences in early expansion assumptions translate into billions of light-years of difference today. James Webb's contribution lies in reducing uncertainty at the most critical point in this chain: the early universe. Before Webb, astronomers often relied on photometric redshifts for very distant galaxies. These are estimates based on brightness and color patterns rather than direct spectral measurements. While useful, photometric redshifts carry larger uncertainties, especially at extreme distances. Webb, by contrast, provides spectroscopic redshifts for many early galaxies. Spectroscopy breaks light into its component wavelengths, revealing precise fingerprints of chemical elements. When those fingerprints appear shifted, the amount of shift can be measured with high accuracy. This precision matters enormously. It allows astronomers to confirm that certain galaxies truly exist at extreme distances rather than being closer objects masquerading as distant ones due to dust or other effects. Webb has confirmed that many of these galaxies are genuinely ancient. Once confirmed, these galaxies place hard constraints on cosmological models. They demand explanations consistent with their observed mass, brightness, and structure at very early times. If a galaxy at a given redshift appears more massive than expected, it implies that matter clumped together more efficiently than models predicted. Efficient clumping requires time, and time within an expanding universe requires space. This feedback loops back into expansion history. Another way Webb refines distance is by improving calibration of the cosmic distance ladder. Earlier rungs of the ladder, Cepheid variables and supernovae, are used to anchor expansion measurements in the relatively nearby universe. Webb's infrared capabilities allow it to observe these objects with less interference from dust, improving accuracy. Dust absorbs visible light, but allows infrared light to pass through. This means Webb can measure intrinsic brightness more reliably, reducing systematic errors in distance estimates. When nearby distances are refined, the entire ladder becomes more stable, and uncertainties at large distances shrink. When uncertainties shrink, discrepancies stand out more clearly. Thus, Webb has highlighted tensions between different methods of measuring expansion. These tensions suggest that our understanding of expansion may be incomplete, particularly in the early universe. This matters because expansion history defines the size of the observable universe today. If the universe expanded faster early on, then the distance to the edge of the observable universe is larger than previously calculated. If it expanded differently at later times, the present-day size also changes. Webb does not yet provide a single revised number for the universe's size. What it provides is pressure on existing models. It narrows the range of acceptable explanations and pushes many of them toward larger scales. There is also an important psychological shift that Webb introduces. Prior to its launch, many astronomers assumed that the largest uncertainties in cosmic size had already been resolved. Webb demonstrates that the opposite is true. The most uncertain region was always the earliest universe, the very region Webb now observes directly. By turning ancient light into precise measurements, Webb connects early cosmic conditions to present-day scale with unprecedented clarity. This connection is why its impact extends beyond galaxy evolution and into the fundamental question of how large the universe truly is. The galaxies that should not exist. When the first deep-field data from James Webb were analyzed, the reaction among astronomers was not excitement at first, but hesitation. The images revealed galaxies at extreme distances, objects whose light had been traveling for more than 13 billion years. That alone was expected. Last, what was not expected was what those galaxies looked like. According to established models, the earliest galaxies should be small, faint, and irregular. In the young universe, matter was only beginning to clump together under gravity. Stars were forming for the first time. Heavy elements were rare. Large, well-organized galaxies were supposed to be the product of long periods of growth through mergers and gradual accumulation. But Webb showed something different. Several galaxies appeared surprisingly bright and massive at redshifts, corresponding to a universe only a few 100 million years old. These galaxies were not diffuse smudges. Some displayed concentrated light profiles, suggesting large numbers of stars packed into relatively compact regions. Others showed signs of chemical enrichment, meaning previous generations of stars had already lived and died. This created an immediate tension. If these galaxies were truly that old and that massive, then the timeline of galaxy formation was wrong. Either galaxies formed much faster than predicted, or the conditions of the early universe allowed matter to organize more efficiently than current models allow. In either case, the implications reached far beyond galaxy evolution. They reached into the size of the universe itself. To understand why, consider what it takes to build a massive galaxy. Gravity must pull vast amounts of matter together. That matter must cool, collapse, and form stars. Stars must then evolve, enriching the environment with heavier elements. Each step takes time, and in an expanding universe, time and space are inseparable. And if massive galaxies exist earlier than expected, then one of two things must be true. Either the universe was denser and more efficient at forming structure very early on, or it provided more volume, more space, for matter to assemble rapidly without interference. Both possibilities imply a universe that behaved differently in its infancy than models assumed. Early cosmological simulations predicted a relatively smooth early universe, with small density fluctuations gradually growing over time. Webb's observations suggest those fluctuations may have grown faster or been larger than anticipated. Faster growth requires either stronger early gravitational effects or different expansion dynamics. Expansion dynamics are directly tied to size. If the universe expanded more rapidly in its earliest moments than models assumed, then by the present day, it would be significantly larger. Even a brief period of enhanced early expansion can have dramatic consequences for present-day scale. What makes these discoveries particularly powerful is that they are not isolated. Webb did not find one anomalous galaxy. It found many candidates across multiple deep-field observations, all pointing in the same direction. The early universe was not empty or primitive. It was already busy. At first, some scientists questioned whether these galaxies were truly as distant as they appeared. Could dust be making closer galaxies appear redder? Could brightness estimates be misleading? These were reasonable concerns, and follow-up observations were required. As spectroscopic data accumulated, many of these objects were confirmed to lie at extreme redshifts. While some early candidates were reclassified, enough remained to challenge the standard picture. The effect did not disappear with better data. It sharpened. This forced theorists to revisit their assumptions. Some proposed that star formation in the early universe was far more efficient than previously believed. Others suggested that dark matter behaved differently at early times, allowing faster collapse. Still others explored the possibility that expansion rates in the first few 100 million years were slightly different than the standard model predicts. Each proposed adjustment carried consequences. More efficient star formation implies denser early regions, which affects how volume and mass were distributed. Different dark matter behavior changes how structure scales with time. Modified expansion rates directly alter the calculation of distances and the size of the observable universe. In all cases, the universe trends larger, not smaller. It is important to emphasize that Webb did not invalidate the standard cosmological model. The overall framework remains intact. What Webb has done is expose pressure points, areas where assumptions were too neat, timelines too clean, and growth too slow. Those pressure points appear precisely where cosmic scale is determined. Another subtle implication lies in the sheer number of early galaxies Webb detected. The early universe was not only hosting massive galaxies, but many of them. A crowded early universe implies a vast underlying volume. Space had room to build complexity quickly, without everything interfering with everything else. This again pushes against the idea of a compact early cosmos. The phrase, "galaxies that shouldn't exist," is not a claim of impossibility. It is a reflection of expectation. These galaxies should not exist according to previous assumptions. Webb has shown that those assumptions must evolve. And when assumptions about the early universe evolve, the inferred size of the universe evolves with them. The discovery also affects how astronomers interpret the observable horizon. If the early universe contained more structure at greater distances than expected, then the horizon we see today encloses more complexity than previously modeled. That complexity does not end abruptly at the edge of visibility. It almost certainly continues beyond it. Webb's galaxies act like signposts. They tell us that the universe did not ease into existence gently. Neuter, it assembled rapidly, energetically, and on large scales from the very beginning. Such behavior is difficult to reconcile with a universe that is only barely as large as we can see. Instead, it suggests a universe that is comfortably larger, one in which the observable region is just a sample, not a representative whole. Expansion changes everything. At the heart of the universe's size lies a single, unavoidable fact. The universe is expanding. Not moving outward into empty space, but expanding in the sense that space itself is stretching. Every large-scale distance in the cosmos is affected by this process, and the way that expansion unfolded in the past determines how large the universe is today. For a long time, astronomers treated cosmic expansion as something that was broadly understood. The details mattered, but the general picture seemed settled. The universe expanded rapidly at first, then slowed as gravity pulled matter together, and more recently began accelerating again due to dark energy. This model explained observations reasonably well, until James Webb began probing the earliest stages directly. What Webb has revealed is that the early expansion phase may not have behaved as smoothly as previously assumed. Expansion is not just a background effect. It competes directly with gravity. Gravity tries to pull matter together to form stars and galaxies. Expansion pulls matter apart by increasing the distance between regions of space. The balance between these two forces determines how quickly structure can form. Before Webb, models assumed that early expansion limited how fast galaxies could grow. Space was stretching quickly, preventing matter from collapsing too efficiently. That assumption placed a natural cap on how massive early galaxies could be. Webb's observations challenged that cap. If massive galaxies already existed when the universe was only a few 100 million years old, then one of two things must be true. Either gravity was more effective than expected, or expansion was less disruptive during that early period, or both. Each option has consequences for size. If expansion was slower early on, then matter had more time to clump locally. But a slower early expansion must be compensated later to reach today's observed expansion rate. That compensation leads to a universe that stretches more dramatically afterward, increasing present-day size. If expansion was faster early on, but structured differently, such as through inflation-like behavior that left behind larger density fluctuations, then the universe would again end up larger today, because early rapid expansion magnifies scale enormously. In cosmology, even small changes early on produce massive effects later. Expansion compounds. A slight difference in expansion rate over a short early interval can translate into billions of light years of difference in present-day distances. This is why Webb's data is so disruptive. It does not merely tweak details. It pushes on the most sensitive part of the entire size calculation. Another factor Webb sharpens is the timeline of expansion acceleration. Dark energy, the mysterious component driving accelerated expansion, dominates the universe today. But its influence in the early universe is still being studied. Webb's observations help constrain when dark energy began to matter and how strongly it affected early structure. If dark energy behaved differently in the past, then expansion history changes, and with it, size estimates. Webb also improves measurements of how uniformly expansion occurs across space. Earlier observations assumed large-scale uniformity, and Webb largely confirms this. But confirming uniformity at extreme distances strengthens the case that the universe extends far beyond what we can see. Uniform expansion implies no special boundary near our horizon. In simpler terms, the universe does not appear to be running out of material at the edge of observation. Structure continues right up to the limit of visibility. This strongly suggests that what lies beyond is more of the same. Expansion also affects how we interpret the cosmic horizon. The observable universe is not static. Its boundary moves as time passes. Some regions that are currently observable will eventually slip beyond reach as expansion accelerates. Others will never become observable at all. Webb's findings imply that the observable region we see today emerged from an even larger region of early space than previously estimated. That early region expanded into the enormous volume we now observe. If the starting region was larger, the resulting universe must be larger as well. This reframes the idea of actual size. The universe's size is not defined by what we can see today. It is defined by the total amount of space produced by expansion since the beginning. Webb's data suggests that production was more generous than assumed. There is also an important psychological shift here. Before Webb, astronomers could plausibly believe that we were approaching the final refinement of cosmic scale. Webb demonstrates that the deepest uncertainties were hiding at the very beginning of time, exactly where Webb now observes. Expansion history is no longer an abstract curve on a graph. It is constrained by real galaxies, real light, and real measurements from the universe's first chapters. As expansion models adjust to accommodate Webb's discoveries, size estimates stretch outward accordingly. the universe becomes not just older in understanding, but larger in implication. The cosmic distance ladder is shifting. Every statement about the size of the universe rests on a chain of measurements. Astronomers refer to this chain as the cosmic distance ladder, and it is one of the most carefully constructed frameworks in science. Each rung depends on the accuracy of the ones below it. When one rung shifts, even slightly, the entire ladder adjusts. Before James Webb, the distance ladder appeared stable. The lowest rungs were anchored by geometric methods within our own galaxy. The middle rungs relied on well-studied stars and supernovae. The highest rungs extended outward using redshift and expansion models. Together, they formed a coherent picture. Webb has not broken this ladder. It has refined it, and refinement at cosmic scales changes everything. At the base of the ladder are nearby distance measurements. These include stellar parallax, where the apparent position of nearby stars shifts slightly as Earth orbits the Sun. When these measurements are precise and largely unaffected by Webb, they establish the foundation of cosmic scale. Above parallax come standard candles, objects whose intrinsic brightness is known. Cepheid variable stars are among the most important. Their pulsation periods are directly linked to their true brightness. By measuring how bright they appear from Earth, astronomers calculate their distance. James Webb observes Cepheids in infrared light. This is crucial because dust within galaxies can absorb visible light, making stars appear dimmer and farther away than they really are. Infrared light passes through dust much more easily. Webb's infrared measurements reduce this source of error. With cleaner Cepheid data, distances to nearby galaxies become more accurate. That accuracy propagates upward through the ladder. The next rung involves Type 1a supernovae. These stellar explosions reach a consistent peak brightness, making them excellent markers for distances far beyond the reach of Cepheids. Supernovae allow astronomers to measure distances across vast cosmic volumes. Webb improves supernova calibration indirectly. By refining Cepheid distances, it tightens the baseline against which supernova brightness is measured. Small corrections here matter enormously when applied across billions of light years. At the highest rungs of the ladder lie galaxies so distant that their distances are inferred primarily from redshift. Here, Webb's precision becomes decisive. Spectroscopic redshifts reduce uncertainty at distances where even small errors previously compounded into large discrepancies. What emerges from this process is not chaos, but tension. Different methods of measuring expansion and distance are not aligning as neatly as they once did. Webb's data sharpens this tension rather than smoothing it out. This tension suggests that something in the standard picture may need adjustment. It does not imply that measurements are wrong, but that assumptions tying them together may be incomplete. In cosmology, this often points to early universe behavior. When the ladder shifts, size estimates shift with it. If nearby distances are slightly larger than previously thought, then distant ones must be larger too. If redshift distances are refined upward, the observable universe expands accordingly. What is striking is that Webb's refinements consistently point in the same direction, outward. The universe becomes slightly larger at every rung. There is no single dramatic revision. Instead, there is a cumulative effect. Each improvement nudges distances upward by a small amount. When applied across cosmic scales, these nudges become enormous. This process also reinforces confidence in the results. Multiple independent refinements converge on similar implications. The universe is not just big. It is bigger than conservative estimates suggested. The latter analogy also highlights why the universe's size cannot be pinned down to a single final number. Each rung depends on models that improve over time. As instruments advance, the ladder extends further and becomes more precise, revealing that previous endpoints were provisional. James Webb represents a major step in this process, but not the final one. Its data has already prompted reanalysis of existing measurements and motivated new observations. The future telescopes will build on this foundation, pushing scale even further. The key takeaway is that the universe's size is not something discovered once and for all. It is something inferred through an evolving framework. Webb has refined that framework at its most sensitive points. As a result, the observable universe appears larger, and the total universe, whatever its ultimate nature, appears even more vast by implication, beyond what we can see. As James Webb sharpens our view of the observable universe, it inevitably draws attention to what lies beyond it. Not because Webb can see past the cosmic horizon, but because what it reveals near that horizon tells us something profound about what must exist outside it. The observable universe is often mistaken for the entire universe. In reality, it is only the portion of space from which light has had time to reach us since the beginning of cosmic expansion. Its boundary is defined not by matter, but by time and the speed of light. Beyond that boundary, the universe does not end. It simply becomes unobservable. What Webb has shown is that the observable universe is densely populated right up to its edge. Galaxies do not thin out as we approach the horizon. They do not fade into simplicity. Instead, they remain numerous, massive, and structured. This uniformity carries an important implication. If structure exists everywhere we can see, then there is no physical reason for it to suddenly stop just beyond the limit of visibility. Cosmology rests on a principle called cosmic homogeneity. On large scales, the universe appears the same in all directions and at all locations. Webb's observations reinforce this principle at unprecedented distances. The early universe, even near the observational limit, looks statistically similar to regions closer to us, just younger. This suggests that the universe beyond the observable horizon is not fundamentally different. It is likely filled with galaxies, stars, and structure just like the region we inhabit. The difference is not in content, but in access. When scientists speak about the actual size of the universe, this is where the concept truly expands. If the observable universe is only a local patch, then the total universe could be vastly larger, perhaps hundreds, thousands, or infinitely many times bigger. Inflation theory strengthens this conclusion. Inflation proposes that the universe underwent a brief but extreme expansion very early in its history, stretching space far beyond what we can ever observe. Even after inflation ended, the universe continued expanding, but the initial burst set the stage for enormous scale. If inflation occurred as theorized, then the region we can observe today is a tiny fraction of the total space created. James Webb's discovery of advanced structure at early times fits naturally into this picture. A rapidly inflated universe provides ample room for early complexity to emerge without contradiction. Webb does not prove inflation by itself, but it aligns with inflation's predictions: large-scale uniformity, early structure, and no sign of a nearby boundary. Each of these points suggests a universe that extends far beyond the visible. Another way to understand this is through perspective. Every observer, anywhere in the universe, would see an observable universe centered on themselves. Each of these observable regions would overlap partially, but not completely. If the universe were only slightly larger than what we can see, this symmetry would break down. We would expect to see signs of an edge, we do not. Instead, the universe appears consistent in every direction. Webb confirms this consistency at earlier times than ever before. The farther back Webb looks, the more uniform the cosmos appears. This leads to a remarkable conclusion. There may be regions of the universe permanently beyond our reach that are just as rich and complex as our own. Entire cosmic histories unfolding without ever interacting with us. From a measurement standpoint, this means the universe's size cannot be captured by a single distance. It must be described probabilistically. We can say how large the observable universe is. We can say the total universe is much larger. But we cannot say how much larger with certainty. What we can say is that every new observation pushing the horizon outward increases the minimum size of the universe. Webb has done exactly that. Before Webb, the observable universe already implied a much larger whole. After Webb, that implication grows stronger. The universe does not appear finely tuned to stop just beyond our observational reach. It appears to continue effortlessly. This is why scientists are careful but firm in their language. They do not claim Webb has measured the universe's full size. They say it has revealed that previous estimates were incomplete. The distinction matters. James Webb has shown us that the universe we can see is not an outlier or a special region. It is typical. And if it is typical, then what lies beyond is likely more of the same, on scales we may never quantify. Is the universe finite or infinite? Once the discussion moves beyond what we can see, it inevitably reaches one of the most difficult questions in all of cosmology. Is the universe finite, or does it extend infinitely? This question cannot be answered by observation alone. Yet observations like those from James Webb strongly influence how scientists think about it. The key to this question lies in the geometry of space. On small scales, space appears flat. The rules of Euclidean geometry apply. Parallel lines do not meet. Triangles have angles that add up to 180 degrees. On cosmic scales, however, space could in principle be curved. That curvature would determine whether the universe is finite or infinite. If space is positively curved, like the surface of a sphere, the universe would be finite but unbounded. Traveling far enough in one direction would eventually bring you back to your starting point, without ever encountering an edge. If space is negatively curved, like a saddle, the universe would be infinite and open. If space is perfectly flat, it could be either infinite or so vast that its curvature is undetectable. For decades, measurements of the cosmic microwave background suggested that the universe is extremely close to flat. Not approximately flat, astonishingly flat. Any curvature, if it exists at all, is smaller than current instruments can detect. James Webb strengthens this conclusion indirectly by confirming that structure and galaxy formation extend smoothly to extreme distances. The Webb supports the idea that space behaves uniformly on the largest observable scales. There is no sign that geometry changes near the horizon. No warping, no compression, no thinning of structure. This matters because curvature would reveal itself through distortions in large-scale patterns. Webb sees none. A universe that is flat to such precision strongly favors two possibilities. Either the universe is infinite, or it is finite, but so large that its curvature radius dwarfs the observable universe. In practical terms, both scenarios mean the universe is far larger than anything we can measure directly. James Webb does not prove infinity, but it pushes the boundary where curvature could hide even farther away. If the universe were only slightly larger than the observable region, we would expect to detect subtle curvature effects by now. So Webb's data suggests that if curvature exists, it lies far beyond our current horizon. That pushes the minimum size of the universe outward again. There is also a deep connection between this question and early universe inflation. Inflation naturally drives space toward flatness by stretching any initial curvature to near invisibility. Webb's observations are consistent with an inflationary universe, one that expanded so dramatically early on that local curvature became negligible. In such a universe, the observable region is a tiny fraction of the whole. Even if the total universe is technically finite, its size could be so enormous that the distinction between finite and infinite loses practical meaning. This is where language becomes important. When scientists say the universe may be infinite, they are not making a dramatic philosophical claim. They are describing the simplest explanation consistent with current evidence. Webb's data does not contradict this explanation. It quietly reinforces it. Another way to frame the question is this: has Webb given us any reason to think the universe ends? The answer so far is no. Everything Webb sees suggests continuity. Structure does not taper off. Complexity does not diminish. The universe does not hint at a boundary. This does not mean boundaries do not exist. It means there is no evidence for them within or near the observable region. The implication is subtle, but powerful. The universe does not appear tuned to human visibility. There is no sign that what we can observe represents a special or complete domain. Instead, it looks like a cross-section of something much larger. From a scientific standpoint, the safest conclusion is not that the universe is infinite, but that its size is unconstrained on the upper end. James Webb has raised the lower bound on how large the universe must be. It has not lowered the ceiling. This is why discussions of the universe's actual size often end without a number. The more precisely we measure, the more we realize that size may not be a quantity with a final answer, only a growing minimum. Dark energy and the stretching of reality. If expansion defines the size of the universe, then dark energy defines how that size changes with time. It is the dominant influence on the universe's large-scale behavior today, yet it remains one of the least understood components of reality. James Webb does not reveal dark energy directly, but its observations sharpen the context in which dark energy operates. And that context matters for cosmic scale. Dark energy is not a force in the familiar sense. It does not pull or push objects through space like gravity or electromagnetism. Instead, it appears to be a property of space itself, causing space to expand at an accelerating rate. The more space there is, the more dark energy there appears to be, and the faster expansion proceeds. This creates a feedback loop. As the universe expands, dark energy becomes increasingly influential. As dark energy becomes more influential, expansion accelerates further. Over billions of years, this effect dominates the universe's fate. Before James Webb, dark energy's influence was primarily inferred from relatively nearby observations, supernovae, galaxy surveys, and the cosmic microwave background. These methods suggested that acceleration began several billion years ago, long after the universe's earliest phases. Webb extends the reach of observation closer to the beginning, allowing scientists to test whether expansion behaved consistently across time. Its discoveries of early, massive galaxies placed new constraints on when dark energy could have become dominant and how strongly it influenced early structure formation. If dark energy had been too strong early on, galaxies would have struggled to form at all. Expansion would have pulled matter apart faster than gravity could assemble it. Webb's detection of early structures suggests that dark energy was either weaker in the early universe or behaved differently than it does today. This distinction matters because dark energy's behavior over time directly affects size calculations. Expansion history is not a single curve. It is a composite of different eras dominated by different influences: radiation, matter, and dark energy. Webb helps refine the transition points between these eras. By showing that structure formed early and efficiently, Webb implies that matter dominated expansion long enough for galaxies to grow. That dominance sets the stage for later acceleration. When acceleration begins, it dramatically increases the present-day size of the universe compared to what it would have been under constant expansion. In other words, even if dark energy did not shape the early universe strongly, its later dominance stretches everything that formed earlier. Galaxies that assembled when the universe was compact are now separated by vast distances because dark energy amplified expansion over time. This means that early complexity and late acceleration combine to produce enormous scale. James Webb's contribution is subtle here, but critical. By confirming that early galaxies were already widespread, it implies that there was more structure to be stretched by later acceleration. A universe that was already busy early on, then accelerated for billions of years, ends up much larger than one that assembled slowly. Dark energy also defines the future horizon of observation. As expansion accelerates, more regions of space move beyond our ability to observe them. Light emitted today from distant galaxies may never reach us. The observable universe does not just grow, it eventually shrinks in terms of what remains accessible. This creates a paradox of scale. The universe becomes larger in absolute size, but smaller in terms of what any observer can see. James Webb's observations capture a moment before that isolation becomes extreme, offering a clearer snapshot of how much exists before it slips beyond reach. Another implication concerns uniformity. Dark energy appears to act uniformly across space. Webb's observations support this by showing no large-scale deviations in expansion behavior across different directions. Uniform acceleration implies that the universe is not shaped by local anomalies, but by a global property of space. This again points toward vastness. Uniform processes operating over visible scales usually operate beyond them as well. There is no reason to expect dark energy to suddenly change behavior just beyond the observable horizon. As a result, dark energy strengthens the argument that the universe extends far beyond what we can measure. Its effect does not taper off near our observational limits. It continues, stretching space everywhere. James Webb does not solve the mystery of dark energy. It does not identify its nature or origin. What it does is provide constraints that rule out some possibilities and sharpen others. Those constraints feed directly into models of expansion and, by extension, size. When astronomers revise expansion models to account for Webb's data, dark energy remains a central ingredient. The revisions consistently push size estimates upward, not because dark energy suddenly became stronger, but because its long-term influence is now applied to a universe that was already larger and more structured early on. The universe revealed by Webb is not one that grew slowly and reluctantly. It is one that assembled quickly and then expanded relentlessly. Dark energy ensured that expansion never stopped, and that everything that formed early would eventually be carried far apart. This combination, early richness and late acceleration, defines the scale of the universe we inhabit. Why the universe has no edge and no center. Whenever the size of the universe is discussed, a familiar image often appears in the human mind. A vast sphere expanding outward into empty space, with an edge somewhere beyond the furthest galaxies. This intuition feels natural, but it is deeply misleading. James Webb's observations do not support the idea of an edge, when they reinforce a far stranger reality, one in which the universe has no center and no boundary, in the way we normally understand those concepts. To see why, it helps to return to what expansion actually means. The universe is not expanding into something. There is no surrounding emptiness waiting to be filled. Instead, expansion means that the distance between all large-scale structures increases over time. Space itself stretches. Every region of space participates equally in this process. From any galaxy, all other distant galaxies appear to be moving away. This is not because that galaxy sits at the center of expansion, but because expansion happens everywhere at once. If observers existed in a galaxy billions of light years away, they would see the same pattern, with themselves appearing to be at the center of an expanding universe. James Webb's observations strongly support this picture. The telescope sees early galaxies distributed evenly in all directions. There is no gradient suggesting we are closer to a center or an edge. The universe looks statistically similar no matter where Webb looks, even when observing regions near the limit of visibility. This uniformity is one of the strongest indicators that the universe does not end just beyond what we can see. If the universe had an edge near the observable horizon, we would expect to see distortions in structure, density, or expansion behavior as we approached it. Galaxies might thin out. Patterns might warp. Expansion might behave differently. Webb sees none of this. Structure continues smoothly up to the observational limit. The absence of edge effects tells us something important. Either the universe is infinite, or it is finite, but vastly larger than the observable region. In both cases, the observable universe is not special. It is a small, typical region within a much larger whole. Another common misconception is that the Big Bang was an explosion from a single point. In reality, the Big Bang occurred everywhere at once. Every point in space was once extremely dense and hot. Expansion began simultaneously throughout space, not from a central location. This means there is no location in the universe that can be identified as the center of the Big Bang. There is no direction one could travel that would bring them closer to an origin point. James Webb's data is fully consistent with this interpretation. Early galaxies appear in every direction, not radiating outward from a single region. The idea of an edge often arises because of the observable horizon. It feels like a boundary. But this boundary is not a physical wall. It is a limit set by time and the speed of light. Beyond it, the universe continues, but its light has not yet had time to reach us, and in many cases, never will. Webb's ability to observe galaxies near this horizon shows that the horizon itself is not a special place in space. It is simply where our information runs out. The universe does not change behavior at that boundary. Our access to it does. This distinction is subtle but critical. The observable universe is not the universe's size. It is the size of our cosmic window. James Webb has effectively cleaned that window, allowing us to see that what lies at its edge looks remarkably ordinary. And when the edge of what we can see looks ordinary, the simplest explanation is that it is not an edge at all. There is also a geometric way to understand this. In a flat universe, which observations strongly support, parallel lines never meet, and space extends without curvature. In such a geometry, there is no natural boundary. Space simply continues. If the universe were curved like a sphere, it could be finite without edges. Even then, traveling far enough in one direction would eventually bring you back to where you started, without ever encountering a boundary. Webb's observations are consistent with both possibilities, but they rule out a small, tightly curved universe. Again, this pushes size upward. What James Webb has done is eliminate many of the last plausible scenarios in which the universe could be only slightly larger than the observable region. The data increasingly points toward a universe that is either infinite or so enormous that any curvature lies far beyond detection. This realization changes how we think about scale. The universe does not have an outside. It does not sit within a larger space. It is the totality of space itself. Asking what lies beyond it is like asking what lies north of the North Pole. The question assumes a framework that does not apply. When people say James Webb revealed the actual size of the universe, this is what they are responding to. Not a number, but a removal of comforting boundaries. The universe does not appear to be a neatly contained object. It appears to be open-ended. Webb's observations make it increasingly difficult to imagine a universe that conveniently ends just beyond our reach. Instead, the cosmos looks vast, uniform, and indifferent to observation limits. The largest structures ever observed. When astronomers talk about the universe on its largest scales, they are no longer describing individual galaxies or even clusters of galaxies. They are describing a vast architecture, an arrangement of matter so enormous that it takes hundreds of millions of light years just to trace a single feature. James Webb's observations do not merely add detail to this structure. They reinforce its scale and continuity, strengthening the case for a universe far larger than what we can directly observe. On the largest scales, matter in the universe is not distributed randomly. Galaxies gather along immense filaments of dark matter and gas, forming a cosmic network, often referred to as the cosmic web. These filaments stretch across space, connecting dense nodes where galaxy clusters reside. Between them lie enormous voids, regions with very few galaxies, spanning tens or even hundreds of millions of light years. This pattern was predicted by simulations long before it was observed in detail. Gravity, acting on tiny density fluctuations in the early universe, naturally produces this web-like structure over time. As matter collapses along preferred directions, filaments form, grow, and interconnect. What James Webb contributes is confirmation that this structure was already emerging far earlier than expected. Webb's deep field observations show galaxies forming along preferred directions even in the early universe. This suggests that the scaffolding provided by dark matter filaments was already in place very early on. Structure was not slowly assembling from scratch, as it was unfolding within a pre-existing framework. The existence of such large-scale organization so early places strong demands on the size of the universe. Filaments and voids require room. They cannot form in a compact or tightly bounded cosmos without producing distortions or edge effects. Instead, they imply a universe that extends smoothly and uniformly across vast distances. Some of the largest known cosmic structures, such as immense walls of galaxies, span distances approaching 1 billion light years. These structures do not violate cosmological principles because they are not solid objects. They are statistical features, regions where matter is more densely arranged than average. Still, their size is remarkable. What matters is not just that these structures exist, but that they appear typical. There is no indication that we are observing a special or maximal feature. The largest structures seen do not cluster near the edge of observation or display signs of compression. They appear as part of a repeating pattern. James Webb strengthens this interpretation by showing that early galaxies already trace this large-scale distribution. The seeds of the cosmic web were present almost from the beginning. This implies that the universe had sufficient scale early on to support the growth of such immense features without crowding or constraint. Void regions are particularly revealing. Voids are not empty. They contain dark matter, radiation, and sparse galaxies. But they are vast, sometimes larger than galaxy clusters themselves. The presence of large voids suggests that matter had ample space to move, separate, and organize over time. What if the universe were only slightly larger than the observable region? Voids of this scale would create noticeable irregularities. We would expect to see anisotropies or asymmetries near the horizon. Webb's observations do not show this. The distribution remains smooth and statistically consistent. Another important point is scale invariance. The cosmic web looks similar at different epochs, scaled appropriately. Webb's early universe observations fit naturally into this pattern. The same underlying structure exists, just at an earlier stage of development. This consistency across time supports the idea that the universe's size was already large enough early on to allow structure to grow without boundary effects. Growth did not have to adapt to a confined space. It proceeded freely. A large-scale structure also reinforces the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. Webb's data supports this principle at earlier times than ever before. Homogeneity implies that no region is special. If no region is special, then the universe cannot be narrowly bounded around us. The largest structures we observe are not approaching a limit. They are not pressing against an edge. They simply exist within a larger pattern that continues beyond our view. This is why discussions of the universe's size increasingly avoid precise upper bounds. The presence of large, coherent structures across immense distances suggests a universe that comfortably accommodates them. The observable universe is not the container. It is the sample. A James Webb's contribution here is not dramatic imagery of single colossal objects, but confirmation of continuity. Structure continues, scale remains consistent, and nothing hints at a nearby end. As our understanding of cosmic structure grows, the conclusion becomes harder to avoid. The universe is not just large. It is spacious enough to allow complexity to arise early and repeat endlessly across regions we will never see. What this scale means for humanity. When the size of the universe expands in our understanding, it does more than adjust numbers in scientific models. It changes the context in which humanity exists, not emotionally or philosophically in a vague sense, but observationally and physically. James Webb's revelations about cosmic scale force a reassessment of how small our observational window truly is, and how much reality exists beyond it. For most of human history, the universe felt intimate. The stars were fixed points. The sky was a dome. Even after the discovery of galaxies, the universe still felt graspable. There were large numbers, but they seemed finite, containable, and increasingly precise. Each improvement in technology appeared to move us closer to a complete map. James Webb quietly dismantles that expectation. What Webb shows is not that humanity is insignificant, but that human observation is profoundly local. We do not see most of the universe. We do not even see a representative fraction. We see a thin slice constrained by time, light, and physics. The universe revealed by Webb suggests that this slice is embedded in something vastly larger than our observational instincts ever prepared us for. This has direct implications for how scientific knowledge is framed. Cosmology often speaks in confident terms: ages, sizes, percentages of matter and energy. Webb reminds us that these quantities are conditional. They describe what can be inferred from within our horizon, not the totality of existence. Humanity occupies no privileged location. We are not near a center. We are not near an edge. We are not positioned where the universe is best observed. We are simply here, at one point in a space that appears uniform, far beyond what we can access. This realization reshapes the meaning of cosmic discovery. Discoveries do not bring us closer to an endpoint. They reveal how far that endpoint recedes. James Webb's data reinforces the idea that the universe is not optimized for observation. There is no sign that cosmic history conveniently aligns with human capability. The universe existed for billions of years before humans emerged, and it will continue for billions more after humanity is gone. The portion we can observe is a fleeting cross-section. This does not diminish the value of observation. It increases it. The fact that a species confined to one planet, orbiting one star in one galaxy, can infer the behavior of a universe potentially trillions of times larger than its visible portion is remarkable. Webb does not highlight human smallness. It highlights human reach. At the same time, the expanding sense of scale imposes humility, and there are limits that can't be overcome by better instruments alone. No telescope, no matter how advanced, can observe beyond the cosmic horizon. Some regions of the universe are not just unknown, they are unknowable in principle. Webb's discoveries make this limitation explicit. They show that complexity does not taper off as we approach our observational boundary. Instead, it persists. This means that what lies beyond is not emptiness or chaos, but continuation. For humanity, this reframes the role of cosmology. The goal is not to catalog everything that exists. That is impossible. The goal is to understand the rules that generate what we see, and to infer carefully what those rules imply beyond our reach. The increasing size of the universe in our models also affects how scientific certainty is communicated. Webb teaches caution, and when early galaxies defy expectations, it reveals how dependent conclusions are on unseen assumptions. Confidence must be proportional to evidence, not familiarity. Another implication lies in timescale. A universe that is vastly larger than the observable region is also one where events unfold on scales that dwarf human planning. Civilizations, planets, even stars are transient. The universe's size ensures that no single event, species, or structure defines its story. From a practical standpoint, this scale has no immediate effect on daily human life. Webb does not change gravity on Earth. It does not alter planetary orbits, but it does change how we interpret our place in reality. The universe does not appear arranged to be fully known. It appears arranged to be partially revealed. James Webb's discoveries also affect how future exploration is envisioned. There is a temptation to imagine humanity eventually spreading across galaxies, mapping the cosmos physically. Webb makes it clear that such expansion would never approach completeness. Even traveling at near light speeds, vast regions would remain forever beyond reach. This does not render exploration meaningless. It defines its scope. Exploration becomes an act of sampling, not conquest. Understanding emerges from patterns, not total access. The concept of an actual size of the universe becomes less about numbers and more about structure. The universe's size is not just large, it is open-ended. Its scale resists closure. Every time observations sharpen, the implied minimum size increases. For humanity, this implies that scientific knowledge is asymptotic. We approach truth, but never arrive fully. James Webb exemplifies this process. It does not deliver final answers. It exposes better questions. This also has implications for how future generations interpret current science. What feels definitive today may appear incomplete tomorrow. Webb's discoveries will themselves be refined, reinterpreted, and possibly revised as new data arrives. This is not failure. It is how understanding grows. The universe revealed by Webb is not hostile or indifferent in a moral sense. It is simply unconcerned with being understood. Its scale does not bend toward observation. Observation must adapt to scale. Humanity's role, then, is not to master the universe, but to listen to it carefully within the limits imposed by physics. Webb's sensitivity allows us to hear fainter echoes from earlier times. But those echoes also remind us of how much remains unheard. The immense scale implied by Webb also reframes debates about rarity. If the universe is vastly larger than the observable region, then the conditions we see, galaxies, stars, planets, likely repeat far beyond our horizon. This does not guarantee life elsewhere, but it expands the context in which such questions are asked. Rarity becomes harder to define when the sample size is unknowably large. At the same time, the observable universe remains precious. It is the only region we can ever study directly. Webb enhances its richness, revealing that even this small window contains extraordinary diversity and complexity. This leads to a subtle but important conclusion. The universe does not need to be fully known to be meaningful. Partial understanding, when grounded in evidence, is enough to reveal structure, law, and continuity. James Webb's revelations about cosmic size do not close a chapter in cosmology. They open one. They signal a shift from a mindset of nearing completion to one of expanding horizons. Humanity stands not at the edge of knowledge, but at the edge of its own observational reach. Aware now, more clearly than ever, that what lies beyond is vast, continuous, and forever beyond direct access. The limits of James Webb and Weiss scale will keep expanding. James Webb has transformed our understanding of the universe's size, but it has not removed the limits of observation. In fact, one of Webb's most important contributions is making those limits clearer. By revealing how much structure exists at the edge of visibility, Webb shows not only how large the universe is, but how much larger it must be than anything we can directly measure. Every telescope is constrained by physics. No matter how large the mirror or how sensitive the detectors, observation is limited by the speed of light and the age of the universe. James Webb does not escape these constraints. It works within them more effectively than any previous instrument, but it cannot overcome them. Webb's deepest images show galaxies whose light has traveled for more than 13 billion years. These observations approach the earliest moments when stars and galaxies could form. But even Webb cannot see the very beginning. There is a boundary where the universe was opaque, filled with hot plasma that scattered light in all directions. Beyond that boundary, direct observation is impossible. Narrow. This means that the earliest expansion phases, the ones that matter most for determining total size, are only inferred, not seen. Webb narrows the range of inference, but it does not eliminate uncertainty. The universe's size remains a quantity constrained from below, not measured from above. This distinction explains why every advance in observational power has historically increased size estimates. As telescopes improve, they do not reveal an edge. They reveal continuity. Each time, the minimum size grows, while the maximum remains undefined. James Webb follows this pattern precisely. Its discoveries force revisions to early universe models, pushing expansion histories toward scenarios that yield larger present-day scales. But those revisions are themselves provisional. They are based on the best available data, on which future instruments will refine further. Already astronomers are planning successors to Webb, telescopes designed to observe different wavelengths, larger sky areas, or finer details. Each will address limitations Webb cannot overcome. None will deliver a final boundary. This is not a weakness of science. It is a consequence of the universe's structure. Scale in cosmology is not like scale in geography. Earth has a surface that can be mapped completely. The universe does not present itself that way. Its size is not a property waiting to be uncovered. It is a consequence of processes unfolding over time. Webb's limits also highlight a key insight. Understanding size does not require complete access. It requires reliable patterns. If the universe behaves consistently across observable scales, and then those patterns can be extended cautiously beyond observation. Webb confirms consistency. The early universe behaves in ways that match, but also challenge, later observations. Those challenges are not random. They push in coherent directions toward earlier structure, faster assembly, and larger implied volume. The absence of anomalies near the observational limit is particularly telling. There is no sign that the universe changes character as visibility fades. That absence itself is data. It suggests that the processes shaping the cosmos are not confined to our horizon. This is why the universe's actual size remains an open concept. It is not unknown because of ignorance. It is unknown because of principle. No observer can access all of space-time in an expanding universe. James Webb makes this clear, not by failing to see an edge, but by showing how ordinary the edge looks. When the farthest galaxies appear just as complex, just as structured, and just as consistent with physical law as nearer ones. The simplest explanation is that the universe continues beyond them in the same way. Webb also clarifies the relationship between size and knowledge. A larger universe does not mean less understanding. It means understanding must focus on laws rather than inventory. We learn how the universe works, not how many things it contains. This shift is subtle but important. It moves cosmology away from questions like, how big is everything? And toward questions like, what kind of system produces what we see? Webb strengthens this approach by revealing early complexity that demands explanation. The size of the universe becomes an implication of behavior rather than a standalone fact. In practical terms, this means size estimates will continue to change as models improve. They will almost certainly grow, not shrink. Each refinement that accounts for early complexity or revised expansion history stretches distances further. There is no indication that this process will converge on a neat, final number. Instead, it converges on a conclusion. The universe is vastly larger than the observable region, and its total extent may never be fully specified. James Webb does not end the search for scale. It marks a transition from confident approximation to careful humility. It shows how much can be learned without pretending that everything can be measured. The telescope's greatest achievement may be that it reframes expectations. Instead of asking when we will finish mapping the universe, we begin to ask how deeply we can understand its rules within permanent limits. This understanding is not diminished by scale. It is enriched by it. As we move toward the final sections of this exploration, attention shifts from instruments and measurements to synthesis. What does all of this mean when taken together? What has James Webb actually revealed about the universe's size? And what has it made clear will always what James Webb actually revealed about the universe's size? By this point, it becomes important to slow down and separate interpretation from evidence. Headlines often compress complex findings into dramatic phrases, but science advances through careful distinction. James Webb did not suddenly measure the universe from one end to the other, and it did not discover an edge. It did not overturn cosmology. What it did was more subtle, and ultimately more important. James Webb revealed that the universe we can observe is denser, richer, and more mature at early times than we previously believed. That single fact reverberates through every calculation tied to cosmic scale. Before Webb, Size estimates relied on a picture of the early universe that was relatively sparse. Galaxies were expected to be small, rare, and slow to assemble. Expansion models were calibrated to that expectation. When the early universe appears emptier, the implied volume required to host it is smaller. Webb overturned that emptiness. The early universe, as Webb shows it, is crowded. Massive galaxies appear earlier than expected. Star formation begins sooner. Chemical complexity develops faster. All of this implies that there was more usable space earlier than models assumed, or that space behaved in ways that allowed structure to emerge more efficiently. Both conclusions in large scale. What Webb actually changed is the minimum size the universe must have. The observable universe was never thought to be the entire universe. But Webb shows that even the observable part contains more complexity than conservative models predicted. To produce that complexity without contradiction, the universe must be larger in its total extent. This is not a philosophical inference. It is a structural one. If the universe were only marginally larger than the observable region, early structure would show signs of compression or boundary effects. Webb sees none. The distribution of galaxies remains smooth and statistically uniform up to the horizon. And this uniformity matters more than any single galaxy discovery. It tells us that the observable universe does not sit near an edge. It sits deep inside a larger domain. James Webb also sharpened our understanding of expansion history. It did not provide a new expansion law, but it constrained the early phases more tightly. Those constraints favor scenarios where the universe either expanded differently early on or where matter clumped faster than expected. Both scenarios produce a larger present-day universe. What Webb did not do is invalidate the age of the universe. The universe is still about 13.8 billion years old. What changes is how far apart things are now compared to where they were then. Age stays fixed. Distance stretches. This distinction is often lost in public discussion. People assume that a larger universe must be an older universe. That is not the case. A universe can be relatively young and extremely large if expansion proceeds efficiently. Webb reinforces exactly this possibility. Another important clarification is that Webb did not resolve the debate over whether the universe is finite or infinite. It does not need to. By pushing the scale where curvature could appear far beyond the observable region, it makes the distinction practically irrelevant. Whether finite or infinite, the universe is far larger than anything we can access. This reframes the phrase actual size. The actual size is not a number waiting to be announced. It is a range constrained from below by observation and from above by theory. Webb raises the lower bound significantly. In doing so, it exposes a pattern that is repeated throughout the history of astronomy. Every time observational limits are pushed back, the universe grows. Not because it physically expands faster at that moment, but because our understanding catches up to its true scale. James Webb is not an exception to this pattern. It is one of its clearest expressions. What makes Webb special is how early in cosmic history it can observe. Previous telescopes refined the nearby universe. Webb refines the beginning. That is where scale is set. When early assumptions change, everything downstream changes with them. This leads to an important synthesis. The universe is not just larger than we thought. It is larger in a structurally unavoidable way. The early presence of massive galaxies, the smoothness of large-scale structure, and the consistency of expansion across direction and time. All of these converge on the same conclusion. The observable universe is not representative of the whole. It is a local window. James Webb has not told us how big everything is. It has told us that everything does not conveniently stop just beyond our reach. It has shown us that the universe does not thin out as visibility fades. It continues. That continuation is the most important revelation. As the evidence accumulates, cosmology shifts from asking, "How big is the universe?" to asking, "How much of it must exist for what we see to make sense?" Webb answers that question decisively, far more than we can observe. The true scale and the limits of knowing. After tracing observations, models, and implications, where the question returns in a quieter form, what can actually be known about the universe's size? James Webb has expanded the answer, but it has also clarified where certainty ends and inference begins. This distinction is not a weakness of cosmology. It is its foundation. The universe does not present its full extent to any observer. In an expanding cosmos governed by a finite speed of light, information is always partial. There are regions whose light has not yet reached us, and regions whose light never will. This means that the total size of the universe is not something that can be directly measured, even in principle. What can be known is the minimum scale required to explain what we observe. James Webb raises that minimum. By revealing a universe that was already complex and populated at very early times, the Webb forces cosmological models to accommodate greater volume, earlier structure, and more efficient expansion. Each accommodation pushes the universe's implied size outward. This does not lead to a final number. It leads to a conclusion about character. The universe is not tightly bounded. It is not delicately arranged around our horizon. It does not appear to be near an edge. Every observation points toward continuity rather than closure. Webb's discoveries also underscore an important methodological point. Cosmology advances not by finding limits, but by eliminating constraints. When something does not appear where it should, such as a thinning of structure near the horizon, that absence becomes evidence. The absence of boundaries is itself data. James Webb shows that the early universe behaves in a way that is difficult to reconcile with a small or moderately sized cosmos. The smoothness of large-scale structure, the early emergence of massive galaxies, and the consistency of expansion across directions all suggest that the universe extends far beyond what we can observe. Whether that extension is finite or infinite remains unresolved, but the difference becomes academic at scales so vast that the observable universe is a negligible fraction. This realization reframes cosmic humility. The universe is not unknowable in the sense of being mysterious or chaotic. It is unknowable in the sense that its total extent exceeds the reach of observation by design. This is not a failure of technology. It is a consequence of cosmic structure. James Webb brings this into focus by showing us how ordinary the edge of visibility looks. There is no dramatic transition, no warning sign, no hint of finality. The universe simply continues until our information runs out. This continuity has a powerful implication. The laws of physics we observe locally likely apply far beyond our horizon. The same processes that shaped early galaxies here likely shaped countless others we will never see. The universe does not appear to change its rules with distance. In this way, understanding size becomes secondary to understanding behavior. We may never know how large the universe is, but we can know how it works. James Webb strengthens that knowledge by connecting early conditions to present structure more tightly than ever before. This connection allows scientists to rule out many small universe scenarios. It allows them to say, with confidence, that the universe must be much larger than the observable region. That is a meaningful and powerful statement. The phrase "actual size" therefore takes on a different meaning. It does not refer to a measurable diameter. It refers to the recognition that the universe's scale is open-ended and resistant to closure. Webb does not finalize size. It dissolves the illusion that size could ever be finalized. In doing so, it returns cosmology to its most honest form. The universe is not a problem to be solved completely. It is a system to be understood progressively within permanent limits. James Webb represents a turning point because it exposes those limits clearly while pushing understanding further than ever before. And it shows that even as instruments improve, some aspects of reality remain fundamentally beyond reach. Not because they are hidden, but because they are too large. As this exploration nears its end, what remains is not a number, but a perspective. The universe is vast beyond calculation, structured beyond early expectations, and continuous beyond observation. A universe larger than expectation, James Webb did not reveal the universe's size in the way a ruler reveals length or a map reveals borders. What it revealed is something more enduring. That every time humanity believes it has approached the limits of cosmic scale, those limits dissolve. The universe does not shrink into definition as understanding improves. It expands. The discoveries made possible by the James Webb Space Telescope do not contradict earlier science. They complete it. They show that the early universe was not a quiet beginning that slowly awakened. It was already active, already structured, already expansive. That early activity demands space. Space that had to exist long before it could be observed. This is the central insight. The universe did not grow large by accident. Its scale is a consequence of how it evolved. James Webb gives us direct access to that evolution at its earliest observable stages, and what it shows is consistency without confinement. The observable universe is immense, but it is not the whole. It is not even close. It is a horizon imposed by time and physics, not by structure or design. Beyond it, the universe likely continues with the same laws, the same patterns, and the same indifference to observation. Webb's legacy is not a new number for cosmic size. It is a correction in how size is understood. Scale is not something that waits to be measured completely. It is something inferred from behavior, structure, and continuity. The more complete the behavior appears near our horizon, the larger the universe must be beyond it. In that sense, James Webb has revealed the actual size of the universe in the only way such a thing can be revealed, by showing that it cannot be comfortably contained by our previous expectations. The universe remains open-ended. Its size is not defined by what we see, but by what must exist for what we see to make sense. James Webb has raised that requirement dramatically. This is not the end of the story. It is the point where certainty gives way to scale, and scale gives way to perspective. The universe is larger than we thought, not because it changed, but because our vision finally reached far enough to realize how much more there is.